is Katherine Gonzalez and I am a student of Salesian Polytechnic University. I am studying systems engineering and now I am going to expose my project of formal languages subject about the transformation of non-deterministic finite automata to deterministic finite automata. To start with my presentation, I would like to give some basic fundamentals of finite automatas. For a long time, the desire to obtain information of data accurately and correctly has been a big problem in the field of mathematics because it is a complex and infinite world where perfection is the goal. However, over time it extended to other fields including the technological, scientific field, among others, where organizing, calculating, and using the data in a good way were done manually. This project allows knowing the operation of the two types of automata that exist, the same ones that meet each one with several requirements, several steps, and different way of solving them, however, having excellent results in the use of treatment of data, in this case based on formal languages. The finite automata. Finite automata are theoretical machines that change their status as they receive values or change in their input. These automatons are limited to two values, accepted or not accepted, which can indicate if the string that has been received as input is valid or not. Generally, we will use the finite automata to recognize irregular languages. That is, a word will be considered valid only if it belongs to a certain language. An automaton is represented graphically in the following way. Ovals that represent each one of the states of the automaton. We have arrows that represent each of the events or transitions of the automaton. The double oval that represent a final state, a sequence of events that took up the be considered acceptable. The arrow represents each of the events of transitions of the automatons. The process to solve a finite automaton is: first, establish the initial state. After, write a variable in the next transition. After, establish the new state. Then, we are going to ask if it is acceptable or not. If it is false or not, we return to write a new variable like that. Or else, we ask if we need other state. If it is true, we return to write a new variable. Else, we establish the acceptance state and finish. The non-deterministic finite automata. A non-deterministic finite automaton is a finite automaton that, unlike deterministic finite automata, has at least one state where there is more than one transition. The process to solve a finite automaton is: first, establish the initial state. After, we write a variable in the next transition, or transitions in this case. Then, we ask if it is acceptable or not. If it is false, we return to write a new variable. Else, we ask if we need other state. If it is true, we return to write a new variable. Else, we are going to establish the acceptance state and finish all. The transformation from Afnd to Afd. The steps that we must follow are: the first one, Determine and identify the elements of the automaton that is presented. Second, add an error status at the end which contains the symbols of the alphabet. Third, create a transition table to get the Afnd. And the last one, once the process of the table is finished, we begin the transformation and obtain the finite deterministic automaton. The process to convert an Afnd to Afd is: first, we must create a transition table. After, we must identify each one of the elements of the automata and put them into the table. After, we ask if exists the state to the next transition. If it is false, we return again, and if it is true, we write it, and we ask again if the table is complete. If it is true, we finish all the process. Else, we return before the first condition. Right here. Now, we're going to do an example about the transformation from Afnd to Afd. For our example, I have chosen an Afnd with 5 states: 1, 2, 3, 4, and 5, and 2 transitions, A and B. Additionally, we have the initial state that at the same time is a final state and the other final state, here and here, that in this case are Q0 and Q1. This automaton is using an alphabet with 2 symbols, A and B. The first step is creating a transition table like this, where we identify the states and the alphabet. Vertically, right here, we must write the states of the automaton, and horizontally the symbols of the alphabet, in this case A and B. Then we start. First, we'll start with our initial state, Q0, where with A we go to Q1, then write it in the table. In the same way, for the second transition from Q0 to Q2, there are an A2, so that's going to write in the table Q1 and Q2. For the transition B, in the state number 1, that is Q0, we haven't transitions, so we don't write anything. After, we go to the second state, Q1, and check the same that before. Here, in this case, Q1 go with A to itself. It's like a recursive process. Then we write it in the table. Yeah, that's okay. We write it in the table and continue. The next part is compare that with letter B, go to the next Now I'm going to do an exercise to explain you the transformation. For our example, I have chosen an Afnd with 5 states, 1, 2, 3, 4, and 5, and 2 transitions, A and B. Additionally, we have the initial state, this one, that at the same time is a final state, and other final state, that is it. This automaton is using an alphabet with 2 symbols, A and B. The first step is creating a transition table where we identify the states in the alphabet. Vertically, we must write the states of the automaton, and horizontally, we must write the symbols of the alphabet that we are using. Then, let's start. First, we start with our initial state Q0, where with A we go to Q1, like this. Then, write it in the table. In the same way, for the second state, with A, go to Q2. Then, write it in the table. After, we check that any state goes to B, so we don't write anything here. After, we go to the second state, that is Q1, and check the same that before. In this case, Q1 goes with A to itself and to Q2. So we write it in the table, and with B there isn't any state, so we don't write anything. We continue, and then we go to Q2, that is here, and check that with A go to Q1, and to B go with Q3, that is here, and Q4. We write it in the table like that. After, we go to Q3, that is here, and check that with A we go to Q number 1, and with B go to Q number 3 and number 4. So we write it in the table. Then we go to the state number 4 and check that there isn't any transition with it, so we don't write anything. Now we have here the table completed with all the information we found before. The next step is create a new table to do the transformation of Afnd to Afd. So first we start with our initial state again, Q0, where with A we go to Q1, then write it in the table like before, and in the same way for the second state we go with A to Q2, and we are going to write it in the table. After, we check that any states go to B, and we don't write anything. After, we take the last states, in this case Q1 and Q2, because it hasn't been verified. We must check each state after of each transition. Now, Q1 with A go to Q1 again, and Q2 with A go to Q1 too. For that reason, it is bold. We don't have to repeat it again, so for that it is bold. Then we do the same with B, where Q1 doesn't have any transition, so we compare Q2, where with B go to Q3 and Q4, here and here. After, we take the last states again, in this case Q3 and Q4, because Q1 and Q2 were validated already. Then Q3 with A here, go to Q1 again, and Q3 with B go to itself, and Q4 like that. The last one is Q1 because it hasn't been verified. So we continue. The last one is Q1 because it is the only that hasn't been repeated. So we check Q1 with A and Q2 anymore. Like that, we have finished. And here we have the table completed with all results. And the last step is to draw the new AFD, like here. Here we have the table with each state and each transitions with a symbol. And like that, we have a new AFD and a better result, more efficient, and we have finished. Thank you.